and welcome back to the session about process control. This video will now focus on so-called model-based control approaches. One specific example of a model-based control concept is model predictive control, or MPC. The idea of MPC is to use the process model for predicting the future trajectory of the process outputs Y across the so-called prediction horizon NP. See the region highlighted in red. An optimization algorithm computes the sequence of process inputs U along the so-called control horizon NC, such that Y tracks R. See the green region in the diagram. When the optimal sequence of process inputs is known, only the current value UK is applied to the real system. At the next time instant, the true system output Y is measured. This measurement of the true system output introduces the desired feedback loop. The horizons are shifted by one time instant, and based on the newly available information, the optimization is performed again. This concept is very flexible in terms of defining the optimization problem. It can easily handle multiple input, multiple output systems and constraints. A prerequisite for using model-based control concepts is the availability of suitable process models. Such process models need to be simple and sufficiently accurate. We are not aiming for the best possible accuracy, but we are interested in simple models that capture the main dynamics of the system. Typically, mechanistic or data-driven modeling approaches are used. The mechanistic ones are based on physical or chemical laws. These laws are used to derive the system equations. Here you see one example. On the left, you see the vertical movement of a particle in y direction in the presence of a gravitational force. It is expressed by mass times g plus the air drag, which is assumed to be proportional to the velocity v with proportional gain kf. The advantages of mechanistic models are the gain of system insight, and that typically only a small number of parameters needs to be selected. However, it is not always possible to derive mechanistic equations. In such situations, data-driven approaches can be a suitable alternative. Data-driven models are derived from experimental data. To create such a model, in the first step, the real system is excited by predefined excitation signals. The response of the system to these inputs is captured. In the second step, this data is fed into appropriate identification algorithms in order to create a system model. One example of such an algorithm that creates a model from experimental data is the so-called local linear model tree, or LOLIMOD algorithm. The obtained model is typically validated against another set of experimental data. The advantage of data-driven models is the applicability to systems lacking mechanistic descriptions. A drawback is a need for a large amount of identification data, which is needed to create the model. Also, this approach reveals less system insight when compared to mechanistic process models. There are also other modeling approaches, which are frequently used in pharmaceutical manufacturing. Let me show you a few examples. One is based on the discrete element method, or DEM. These models can be used to simulate particle systems in a mechanistic framework, and they are well suited to perform simulation studies. Also, population balance models, or PBMs, are frequently used to describe, for example, the particle size distribution of granules when they propagate through a unit operation. For model-based control, these two approaches are not suitable, since they are computationally too complex. Appropriate model reduction techniques can be used to derive models that are suitable for model-based control. Besides these detailed models, so-called multiple linear regression models, or MLR models, are often used to select the operating points of pharmaceutical unit operations. They are typically based on steady-state data, which means that they are static models and therefore cannot capture dynamics of the system. Consequently, they cannot be used for model-based control. With this overview of model-based control, I would like to thank you for your attention and see you soon.